Hi, this video is going to be about areas bound by the x-axis. So we're going to be using definite integrals here, as when you're showing the fundamental theorem of calculus, the connection between integration and a function was that it provided the area underneath a curve. So when we use the language bound, what we're talking about is, say we've got, for example, on some axes, we've got some function, and the area might be given the x-axis, right, is down here on the bottom. The area bound between the curve and the x-axis from some certain x values, right, from, in this case, from 0 up to here. We're looking at this area under here. Okay, but of course this one that I've drawn here is bound by the y-axis as well. So suppose we've got just something even more generic. We've got a function and we're looking between a certain x and x values here, a and b. Then this area here is going to be the integral from a to b of the function. But there's going to be one small caveat that I'll add to this in a moment. So if you look over here, you can see I've got some questions I'm going to go through, and these will all illustrate something a little bit differently. So it says find the area bounded by the x-axis and these other equations or x values. So sometimes these questions are provided a diagram alongside them, but sometimes they're not. So I'm going to assume the worst, that we don't have a diagram, and so what we should do with all of these is, first thing we do is get into that bit of just drawing a diagram. So here we've got find the area bounded by the x-axis and y equals x is a straight line here, and from x equals 0 up to x equals 2 we're looking for this area here. Now I've purposely chosen a basic geometric shape so that we can work out its area just using a normal area of a triangle formula, right? So if we're going to need the height for this triangle, so if the x value here is 2, well then the y value, the height of the triangle at that point, is also going to be 2. So just using area of a triangle formula would be half times the base is 2 times the height of 2 is going to be, half of 2 is 1 times 2 is going to be 2, and because it's area it will be square units, whatever they happen to be. Okay, so now we're going to try the same thing, but using calculus. Okay, so we've got the area is going to be the integral from 0 to 2 of x dx. The integral of x dx is add 1 to the power x squared on 2, and we're going from 0 to 2. So this is going to equal, substitute 2 in, 2 squared on 2 minus 0 squared on 2, and we get the same thing. 2 squared is 4 on 2 is 2, minus 0 is 2. So we get the same thing using just basic geometry, I suppose, and also by using calculus. So the next three are going to be the exact same triangle, but just we're going to investigate what happens in the different quadrants. So for question 2, we've got, this time we're still bound by the x-axis, and we're doing the graph y equals negative x, which is like this, and we're going from x equals negative 2 to x equals 0 there. So we're looking at this area here. Okay, so of course this would be the exact, because of the symmetry, right? This is the exact same triangle as in question 1. It's got a base of 2 and a height of 2, so using area formula, it's going to have an area of half times 2 is going to be 2. Okay, but again, we can do this with calculus, so we'll find the integral from negative 2 to 0 of negative x dx. Now the negative we can take out the front and integrate x dx. So we've got negative, and the integral of x is same as before, x squared on 2, add 1 to the power and divide by the new power, and we're going from negative 2 to 0. So then we've got negative, and now we're going to sub in 0 squared on 2 minus negative 2 squared on 2. And this will be negative 0 squared on 2 is 0, minus negative 2 all squared is 4 on 2 is 2. So negative 2 becomes positive 2. Alright, so that's in the second quadrant. So notice the similarity with 1 and 2, right, in terms of which quadrants we're looking at. 1 is the first quadrant, 2 is the second quadrant, is that they're both above the x-axis, and that's important. The next two examples are going to be below the x-axis, and we'll see something slightly different with them. Okay, so here's number 3. So we've got the area bounded. By the way, another word for bounded is enclosed, is sometimes, it's closed in by these things. Okay, y equals negative x, so same equation as before, y equals negative x, and x equals 0 is here, to x equals 2. So this is the region that we're looking for. So let's integrate this. We'll integrate from 0 to 2 of negative x dx. So this is the same as negative whatever the integral of x with respect to x from 0 to 2 is. Again, integral of x is add 1 to the power, divide by the new power from 2 to 0. So we'll get negative, sub in 2 squared on 2, minus 0 squared on 2 is going to be negative 2 squared is 4 on 2 is 2, minus 0 is going to be negative 2. Now, so this is why I alluded before to the fact that we're going to have to add a small caveat. Because of the way that the definite integral is defined in the fundamental theorem of calculus, it means the area is given if it's as positive if it's above the x-axis. So that's why with examples 1 and 2, we saw that when we calculated the area using the definite integral, we got a positive 2 units, positive 2 units. But here, when we calculated the area, we get negative 2. But again, with the symmetry, obviously it's the same triangle with a base of 2 and a height of 2, right? So the area of that triangle, enclosed in by the x-axis, from 0 to 2, is obviously 2. So how can we make negative 2 into positive 2? Well, we can take the absolute value of it. Right, so if we go back up to the top, really, let's just modify what we set up here. The area of a curve from A to B is actually going to be the absolute value, which if it's above the x-axis, it's not going to make a difference, right, because it'll already be positive anyway. But if it's below the x-axis, it'll be the absolute value. So just whatever negative value you get, change it into a positive value. Okay, so that means really here, this whole time we should have had absolute value of, whoops, wrong side of the equal sign, absolute value here, absolute value of this thing the whole way through Okay. So question 4 is going to be very similar in that it's going to be below the x-axis, but this time let's just try doing it with absolute values the whole way through. So let's draw it up. We've got the graph of number 4 is the graph of y equals x from -2 to 0. So we're looking at this area here. So the area is going to equal the integral from -2 to 0 of x dx, but since it's below the x-axis, or just to be safe, we're going to take the absolute value of whatever that is. Okay, so again, same integral. And when we sub in, we get 0 minus 2. So we actually get 2 square units the whole time. Okay, so what about if we're going, for example, question 5, we're now going, rather than being really, in all these examples 1 to 4, we've been stuck, we haven't gone past the y-axis either, right? But what happens if we're going past the y-axis? So question 5, we've got the line y equals x, and we're going from -2 up to 2. So what this means is, what's the area, right, from -2 to 2 bound with the x-axis? Well, over here it's this piece here, and we've also got this piece here. So again, these are the same size triangles before, and we've got 2 of them, so if the area of one of them is 2, then 2 of them together will be an area of 4. So let's just have a bit of an experiment. Let's try finding the area from -2 to 2 of x dx. So we'll integrate over this range. We'll substitute in 2 minus subbing in -2. And what do we get? 2 minus 2 is 0. Now, even if we had the absolute value the whole way through, it still would have been 0, right? So, what we need to do is break it up into different pieces, right? There's really the -2, oh sorry, I'm reverse, I got to go the other way. -2 to 0, that piece we can integrate like we just did, it was the bit from above, and then from 0 to 2 was also in one of the other questions above. So the problem with doing this is that because if we, as you saw, one of these, if you find the definite integral of this piece here, it's 2, and the definite integral of this piece here is -2. So when you add these two areas together, you get 2 minus 2, and because they're equivalent, they cancel each other out. So if you want to find the area here, you have to actually split them up, and then this one isn't too bad because it's above the x-axis, but then you'll need to take the absolute value of this piece. So to find the area, we've got to actually split it up into the two pieces. So we'll go from -2 to 0, and that is the bit below the x-axis, right? This is this bit here. So because it's below the x-axis, we'll have to take the absolute value. and then we're going to add on the other piece here. So this comes from, right, this piece here comes from there. So we've already done these calculations above, so I'm not going to repeat them. We've got 2 plus 2 is 4 square units, as expected. Now, you might notice something about this function, and the reason why the two pieces, sorry, I'm gonna have to get used to this. I won't try to use my hands. The why the piece above and below perfectly cancel each other out. Well, y equals x is an odd function, right? Because if you flip it over the line y equals negative x, that piece there flips over there, or if you rotate it 180 degrees around the origin, then it perfectly lines up, right? So it's an odd function. So something else you can do, particularly with odd functions, is for an odd function, notice here we ended up with 2 lots of the area of one of the pieces, right? Because the areas are the same, we actually ended up with this area twice, over here and over here. So for an odd function, if we're integrating from negative a to a, right? So notice here, like we've got negative 2 through to 2. Alright, so the same value, the same numerical value, but negative and positive, then we can find the area by going from 0 to a, so like we did 0 to 2 here, the integral of the function. And because once we do the one on the other side and take its absolute value to force it to be positive, we get the exact same number. So we've actually got, whoops, oh, teleported. We've actually got 2 lots of that. So, question 6 is intentionally another odd function. So rather than breaking it up into 2 pieces, like we did here and adding them separately, let's just try using the fact by identifying it's a cubic an odd function, and then doing this here. So we've got y equals x cubed. So again, let's draw a diagram to visualize it. This is y equals x cubed, and we're going from negative 2 to 2. So since we're going from the same number, negative to positive, and it's an odd function, right? So those 2 conditions need to be met, that it's an odd function and that it's going to the same numerical values. We can find the area here by doing 2 lots of whatever the area of this piece is here, right? This bit I'm highlighting in yellow, right? That's that area there, and since it's an odd function, we can just double whatever that is. So we'll get 2 lots of integrating x cubed with respect to x, add 1 to the power, and divide by the new power from 2 to 0. And we're going to have 2 times subbing in 2. And what's 2 to the 4? 2, 4, 8, 16 over 4 is 4. So we've got 2 times 4 minus 0 over 4. So we'll get 8 square units. Alright, so question 7 is x squared, so that's not an odd function, it's another special type of function, it's an even function. So let's just have a look and see. Whoop. Let's just have a look and see if something similar or different happens with even functions as with odd. So again, let's draw up the sketch. So this is y equals x squared, and we're integrating from -2 to 2, and the region below that curve bound by the x-axis. Alright, so let's just take the same approach we did by breaking it into pieces. So the area for the first bit, sorry, let's actually do what we did at the start and just investigate. Let's just try taking the integral from -2 to 2 and see if it actually gives us a non-zero area, right? The other one we did with the straight line, we integrated and we got an area of 0, which it obviously wasn't, so that kind of triggered that, oh, maybe this approach isn't correct. So if we do x squared integrates, add 1 to the power, divide by the power, and now we're going to substitute in 2 cubed minus subbing in -2 and so 2 cubed is 8 on 3 minus -2 cubed is -8 on 3, and 8 minus -8 is plus 8 is 16 on 3, which is what's that? 5 1/3. So that answer actually seems a bit reasonable, since it's not 0. Now, why is that? Well, if we broke it up into pieces like we did with the other functions above, the odd ones, well, if we broke it from 0 to 2 and found that integral there, and then did from 0 to -2 this piece here, they're both above the x-axis, so they'd both be positive, so they're not going to cancel each other out. So there's no problem here if it's an even function like this. However, because it is still symmetrical, obviously this piece under here, 0 to 2, is going to be the same as this piece from -2 to 0. So kind of, if you want to, you can get into a habit for even functions as well. The same rule will apply. The only difference is you don't have to use it for even functions, but odd functions, if you don't use it properly or don't break up the pieces and take the absolute values properly, then you will get an area of 0. So for even functions, again, if we're going from -a to a, so like above -2 to 2, same value, but negative and positive, then the area will equal 2 lots of from 0 to a. Right, so same principle of with odd functions applies to even ones as well. So question 8, very similar to question 7, but we'll just try using this approach instead. So what do we got? Question 8. Uh, 3x squared plus 6, so this is going to be a parabola. What does the 6 do? The 6 is going to move it up 6, and the 3 is going to make it steeper. So it's going to look something like this. Right, but because it hasn't shifted left or right, and it's a parabola, it's an even function. It's symmetrical if we flip it over the y-axis. So if we're finding the area under the curve from, I didn't make that line up properly, -2 to 2, right, we can find this area by finding two lots of the area from 0 to 2, because we're going from -2 to 2, the same bit. So we've got two lots of from 0 to 2 of our function is 3x squared plus 6, integrating with respect to x. So if we integrate this, 3x squared, add 1 to the power is x cubed, divide by the new power is by 3, so this will end up with x cubed. 6 integrates to, since it's a constant, 6x. And we're going to go from 2 to 0, or 0 to 2 rather. So we're going to have 2 cubed plus 6 times 2, minus subbing 0 in, 0 cubed plus 6 times 0. So I would actually get into the habit of putting these in brackets. It doesn't, sorry, no, it doesn't matter. It will matter here, right? Because notice when you substitute, sorry, no, it won't matter because it's 0. If this number wasn't 0 here, right, if this was 1, 6 times 1, then when you do negative, whatever this will be negative, but negative times a positive will make this negative. But if you don't put it in brackets and you're integrating multiple functions at once, you might go, okay, plus, minus, and then plus, when it should actually go plus, minus, and minus. But that's just a general thing for definite integrals anyway. So this will be 2 times 2 cubed is 8, plus 6 times 2 is 12, minus 0, 8 plus 12 is 20, times 2 is 40 square units. Okay, so that was odd and even functions. So 9 is something a little bit different. Oh, I've drawn that too far to the side. Oh no, I haven't. I've just scrolled over. So 9, sine x from 0 to 2 pi. So let's sketch sine x from 0 to 2 pi. What's in the middle? Pi. Now, what's going to be the problem if we just integrate integrate sine x from 0 to 2 pi? Well, the problem is this bit here and this bit here have the exact same area, but because this bit's above the x-axis, it'll be positive, and when you do this bit below the x-axis, it'll be negative, and so they're going to cancel each other out. So this is another circumstance where you need to actually draw up the function and have a look at it visually of what's happening, right? I would never be doing any area questions just by looking at what's written in the question here. Always need a diagram, extremely important, right? So here you can notice that they're the exact same area. So you could double one area, but just for the sake of it, let's split it up into two pieces. So let's do this piece here in yellow will be the integral of sine x from 0 to pi. Alright, this bit's from the yellow, and this bit down here will be the integral from pi to 2 pi of sine x, and since it's below the x-axis, we need to take the absolute value. Right, the yellow one, I mean, you can just get into a habit of always taking the absolute value, but the yellow one will be a positive number, so it'll be okay. But the green one, because it's below the x-axis, we need to take the absolute value. Okay, so sine x integrates to negative cos x. And again, Sin x integrates to negative cos x from pi to 2 pi. We're going to make sure we take the absolute value of that piece. So subbing in negative cos pi minus negative cos of 0 plus absolute value of negative cos of 2 pi minus negative cos of 0. Now these you can put this all in your calculator at this point, as long as your calculator is in radians mode. However, I'm just going to draw a very dodgy sketch of this is cos x, so that's 2 pi and that's pi, and this is 1 up here and negative 1 down here. So negative cos of pi, well cos of cos of pi is negative 1, so negative 1 minus negative minus cos of 0 when x is 0, cos of 0 is 1, plus absolute value of negative cos 2 pi, well cos 2 pi is 1, minus cos 0 is also 1, so this becomes negative 1 is 1, plus 1 plus absolute value of negative 1 plus 1. Oh, hold up. I've done something wrong here, because that should be 2 as well. Sin x integrates to negative cos x, negative cos 2 pi. Oh, sorry, that's why. That should be from 2 pi, and then that should be pi. And then we've got so minus negative, and there's a lot of negatives here. Cos pi is negative 1. So minus 1 minus is, so that becomes 2 cancel out to be plus, so that's minus 1, so minus 1 minus another one is minus 2, and so we get 1 plus 1 is 2 plus absolute value of negative 2 is 2. Altogether we get 4 square units. So the reason I didn't do 2 pieces is, don't know why that square is black, that you should be able to break up a function into different pieces when you see it above and below the axes. The reason being, I've only really done ones where it's symmetrical at the moment, but let's just imagine we did a function that's a cubic, right, and let's say we're going from something like from 3 to negative 1. So this isn't, it's an odd function, right, but it's not, we're not going from, negative a to a, right? We're going from negative 1 to 3. They're not the same number. They're not both 1, they're not both 3. So the problem here is that if you integrate from negative 1 to 3, this piece here is going to be negative, and so it's actually going to cancel out this bit up to 1 here. So even though if you integrate this, you're going to get a non-zero number, it's going to be incorrect. So for this one, for example, you'd want to break it up into from negative 1 to 0. And then integrate from 0 to 3. Right, so if you want, you can have a go and try that one yourself. So we'll call this maybe number 10. So there's one to try for yourself, and if you need help with that, ask me. Now again, it's not as bad with an even function, right? Because if we were going, say, from x squared from 3 to negative, oh, it's not really drawn. I mean, they're just rough sketches to visualize it, but 3 to negative 1, because it's an even function, right? Everything's above the x-axis here. Sorry, it really, let me clarify. Even function, it should still be, we should still take the absolute value. Actually, did I write that in here? Let's just be safe and always take absolute values. Why not? The ones I've been using are all, I've just been using x squared as an even function, which is above the x-axis, but we could, of course, it's going to annoy me. That made it worse. Yeah, it's close enough to the middle. We could have an even function below the x-axis. So if it's below the x-axis, then we'll need to take absolute values because it'll be negative. But just the point about even functions, you can integrate. For example, this one would be safe to go from -1 to 3 without breaking it up, right? So if you want to have a go at that one, we'll call that one 11. So this one would be this one sorry, you don't need to break it up into 2 pieces, but this one you would, because there's some above and below. And what about another scenario where there's some bits above and some below either side? Let's go. This is, let's say it's x cubed, and we've moved it up by 2. And let's go from -1. I'll just do the same range here. -1 to 3. Call that 12. Maybe you can have a go at that yourself and have a think about whether you need to break it up into certain pieces. Sorry, just to clarify, this 2 here is the, whoops, well, that doesn't help. Just deleted the actual curve. This 2 here is referring to the y-intercept there. Is -1 actually above or below the x-axis? Well, if you sub in -1 to the function, you get -1 cubed is -1 plus 2 is 1. So the y value of this point here, this is the point -1, comma 1. So there is some, when you're drawing a graph, have a think about, can't really see that, can you? Graphically, whether that should be above or below. I mean, we're just drawing rough sketches just to visualize them, so that's why I haven't put in, for example, every single point and the x and the y axes, because we're trying to visualize it. But again, have a go at this one yourself, and yeah, if you have any problems with 11, well, can I scroll up? These ones that I've scribbled up here, 10, 11 and 12, right? So if you, there you go, that fits them all in. Try having a go at those, and if you need help with them, then post a question under wherever this is posted in Google Classroom. Alright, bye.